So we've seen that when you have an electron trapped on a wire, that's one-dimensional. And you need one quantum number to label the wave function. Now we've got a flat plane, like a drum head. The waves on a drum head need two quantum numbers because they're two-dimensional. You need one in the x direction, one in the y direction. You can guess that when we go to a three-dimensional object like an atom, that we're going to need three quantum numbers, one for each direction, x, y, and z. And you can set the math up so that you're doing that. But it turns out it's easier when you're talking about atoms to use something called spherical coordinates. Spherical coordinates tell you how far the electron is away from the nucleus, that's one coordinate, and at what angles it is to the x-axis and the z-axis. Those are two other coordinates. We don't have to know too much about the details of those, but just know that these quantum numbers are not going to be labeled x, y, and z. They're going to correspond kind of to math and spherical coordinates. So what are the quantum numbers? Let's talk about the first one. It's the principal quantum number. And it's given the symbol N. And it determines the size and the energy of the wave function, the electron wave function. Now, when I'm talking about these three-dimensional electron waves, I'm going to introduce a vocabulary word so I don't have to keep on saying electron wave function or electron wave. I am going to call these orbitals. Okay, so I'm going to use this word from now on whenever I'm talking about an electron wave. It's an orbital. So what do these orbitals look like? Well, let's draw some. If I put the nucleus there, the nucleus is that dot. The wave in three dimensions is going to look like a sphere around it. Now, since it's in three dimensions, it's going to be a little bit more complicated. I'm not going to draw it with showing the amplitude. I am going to draw it showing where there's highest probability of finding the electron. Or if you want to think about it like this, where there's a bigger concentration of negative charge. So think of an orbital, you can think of an orbital as kind of a negatively charged cloud. And the cloud is thicker where the amplitude is highest, which happens to be close to the nucleus. So you get this cloud of negative charge here that gets thicker and thicker as you go in. And it just very slowly, in fact exponentially, dies off. So there's not like a hard surface on this thing. Now you can go ahead and draw a spherical boundary around this and say 99% of the electron charge is inside the sphere. So you'll sometimes see people draw an orbital like this. Like a sphere. And there's the electron in the center. And this, imagine this is in three dimensions. I mean, this is actually a sphere here that we've got, you know. And this is like a container that contains that fog. The fog looks like this. You could draw the orbital either way. And this is actually what the orbital looks like when n equals 1. What happens when n equals 2? Well, from what I've said here, you can figure that you're going to get a bigger orbital, and it's going to have more energy. Now, in the last video we saw that you can increase the energy of an orbital or an electron wave by putting more nodes in it. So when you have n equals 2, you can put a node in it. So here's the nucleus, and the way the nodes go in when you're increasing n is they're radial nodes. So imagine this is a surface of a sphere here. That's a radial node. When we had one-dimensional wave functions, the nodes were points. Two-dimensional wave functions, the nodes were lines. In 3 dimensions, they are planes, or they are surfaces. Alright, so I have this like spherical surface here, and really this should be kind of, if I drew it right, the nucleus would be exactly in the center. And you're going to have this negatively charged cloud here, but remember the amplitude has got to be 0 whenever you have a node. So it's going to be real thick, the negative charge there. And it's going to kind of die off when it hits the node. But with this one, there is another cloud, and this is spherical. You're kind of seeing a cutaway view of it. When you're taking notes, draw these pictures. The act of drawing them kind of gets them in your head a little bit better. So there's kind of a dead spot where this radial node is. And this would be n equals 2 orbital, what it would look like. It's bigger and it's got a node in it, so there's a higher energy than the n equals 1. If you have n equals 3, you can kind of guess what that's going to look like. Here's the nucleus. You're going to have not just one radial node, you're going to have 2. And you'll have a cloud in there. Then you'll have another like cloud outside. And these are like concentric spheres. Now think about this, my drawings here, as though you're seeing an onion cut in half. Onion has all these layers, right? These orbitals are like an onion. They're spherical, and they have a lot of layers. So this is what it would look like if n equals 3. Alright, a cross section of it. Now, you might, like I said, they look like onions, and you can think of these things sort of as shells. It's like, this is like one shell. This has like 2 pieces, 2 shells to it. And this has 3 shells. And they refer sometimes as electrons with n equals 1. They'll talk about electrons that have n equals 1 as being in the first shell. If it was n equals 2, they'll say the electron is in the second shell. Now, you can see that that's not quite accurate to think about this as being the second shell, the ring outside the radial node here. Because when n equals 2, it also includes what's in there. But you can kind of see where they're getting this kind of terminology. If you have an electron with n equals 3, say it's in the third shell, see? So this is how people talk about electron waves that have these different values for the principal quantum number. What values can the principal quantum number take on? Well, the smallest possible value is going to be n equals 1. So n can be 1, it can be 2, it's got to be an integer. It can be 3. How high can it go? As high as you like. It can go up to infinity, but it has to be an integer. Okay? Alright, in the next video we'll talk about the next quantum number.